Hello everyone and welcome to today's lecture. Today we're going to be defining what's called the triple integral, which is essentially the definite integral of a function of three variables. So we can take all of the ideas from what we learned from doing double integration and almost directly apply these ideas to the triple integral, to functions of three variables, which is very, very important because as you know, we live in three spatial dimensions, and very often serious applications, require us to consider the definite integral not only of functions of two variables, but of functions of three variables. So in general, for the triple integral, we're going to consider two things when we're taking a triple integral. Two main things, I should say. We're going to have some domain in three-dimensional space. This domain is bounded by some surface that we call the boundary of the domain. But in general, we have some shape in 3D, and typically in my notes I'll call this what's called omega. So I'll just use the Greek symbol capital omega to denote some three-dimensional domain. So we have this three-dimensional set of points that we're going to consider the definite integral of another function, so some function of three variables. So we have a domain that we're going to be integrating over, and we have some function of our three variables, so of x, y, and z, which I'll just call f, some function f. Just like in 1D, where we define the single variable integral, and also in 2D, where we define the double integral, we want to be able to figure out a way of calculating the accumulation of a function of three variables. Because in both the case of a single variable function and a double, so a two variable function, the definite integral of that function is just the accumulation of that function. So we're going to use a similar notation for this that to what we did before for the double integral, only the triple integral is going to be three integral signs. And so whenever you see three integral signs together, this means the triple integral. Then it's going to be of whatever function of three variables we're talking about. And this is going to be with respect to volume instead of area. For the double integral, our differential was an area element. For the triple integral, it's going to be dv, which stands for volume element. And we'll see why in a little bit when we look into how this is actually defined exactly using a limit of Riemann sums. But it's going to be a very, very similar process to the one we used for a double integral. And we also have to specify what domain we're taking the triple integral over. So in this case, we put omega down here because this denotes that we're taking the triple integral. This notation reads that this is the triple integral of this function of three variables over the domain omega with respect to a volume element. And what this stands for is the accumulation of the function f inside the region omega. So the total accumulation of the function, whatever it's representing, f of x, y, z, inside the region omega. And just like before, we're going to see that this can be used in a variety of different applications. The main two big applications that we'll talk about are going to be the total mass and total charge of a three-dimensional region. But you can use this as well to define the center of mass or the center of charge in a region, as well as the moment of inertia of a three-dimensional object. It's a very, very powerful tool. There are many, many different applications that we can do. In the lecture on applications, which will be in a couple lectures, we'll see all of those applications. But there are even many, many more applications than just the ones we'll go over. We'll go over some of the basic applications, but really there are uncountably many applications of this idea, just like there are for the double integral and even for the single variable integral in Calculus 1. So the main idea, and the way that we exactly define what this value is through the process of Riemann sums. And the idea here in doing the process of Riemann sums is going to be the exact same idea as before for the double integral. The idea is that we kind of cut up our region into all of the individual coordinates. So we have to form a partition here, and the idea is that this region in general is going to go from, say, the minimum value of x in the region is a. That corresponds to this value right here, which is the x coordinate of this minimum value in the region. Maybe a is a little bit closer to the origin here. So like right here. And then the maximum value of x in the region, about right here. So we'll call this b. And the same thing is true for y. You'll have a minimum value in the region and a maximum value for y in the region. I'll call that c and d. It's the maximum value of the y coordinate. And then likewise you'll have a maximum value in z and a minimum value in z, this region, which I'll call e and then call f. So the idea here is we form a partition similar to how we formed a partition for the double integral, where we cut up these intervals into a whole bunch of very, very small pieces. And for simplicity, what we'll do is we'll say that we have the same number of cuts, so n pieces in this partition along x. We'll say we have n pieces in the partition along y, and n pieces in the partition along z, where the width of each piece or each cut along x we'll call delta xk, and the width, actually I think what we'll call it is delta xi. So this is the width along cut I along the x-axis. The width along the cut, the jth cut of the y-axis we'll call delta yj, and then the width of the the kth cut along the z-axis we'll call delta zk. This is the z-axis, and this is the kth cut of the z-axis in the partition. So really what this is doing, and I don't want to draw out all of the cuts like I did for the double integral, but basically you have a bunch of cubes that are kind of cutting up this region in our partition. Each cube, say also the ijkth cube, we'll just kind of draw that right here, be about right here. So this cube is going to have going to be a cube, and we'll kind of zoom in on that. So we'll get a zoomed in picture of that cube. So you have, in general, a number of these different cubes. You're going to have, in general, n cubed if you have n cuts or n pieces along the x partition, n pieces along the y partition, and n pieces along the z partition. You have a very large number of cubes. But each cube is going to be, say, if this is the ijkth cube, this is going to have a width of delta xi, a depth of delta yj, and a height of delta zk. And in each one of these cubes, we also have to pick a point inside the cube to be a sample point. It can be anywhere inside the cube, just like we did for the double integral as well. So this is our sample point, say, inside the cube ijk. You have to sample the function at that point. So it'll be f of xi star, yj star, and zk star. So the Riemann sum is going to be the following summation. This is going to be the approximation to the actual value of the triple integral. And it's going to be a triple summation. It's a summation over every single one of these cubes. So the sum from I equals 1 to n, from j equals 1 to n, and from k equals 1 to n. It's a summation over all of these cubes of the value of the function at the sample point inside the cube times the size of the cube, which we'll call delta v ijk. And we know that delta v, because this is just a rectangular cube, delta v ijk is going to be equal to delta x, or delta z k, delta y j times delta x I. Just the product of each one of these values. So this is the correct way of writing a Riemann sum in general for a triple integral. Now you have to sum over all of these cubes. Nice visualization of this. Again, and I don't want to draw out multiple cubes in the drawing above because it'll just take a little bit too long. But I kind of made up this nice little visualization right here to kind of help you see how this is, again, these cubes are not over this entire region right now, but or in this picture, but you got to kind of take this visualization and visualize all of these cubes kind of stacked on top of each other, extending all the way up and all the way over to from the left to the right, and so on and so forth. Right? So this is in general what a Riemann sum approximation is for a function of three variables over a domain in 3 dimensions, three-dimensional domain. And so the idea here is that you want to remember that this is a triple sum, so it's even larger than the double sum that we encountered for the double integral. This is going to have, in general, n cubed terms in it, because you have to sum over, it'll be the function at x1, y1, z1, and star because it's a sample point, times the volume of the first cube, and you have to add to that f of x1, y1, z1 times the volume of the 112 cube. You have to go all the way up to f of x1 star, y1 star, zn star times the volume of the 11n cube. But that's not done. You're not done yet because you have to add in now all of the combinations for f of x1 star, y2 star, z1, and so on and so forth. Okay, this has a lot of terms in this sum. That f of x1 star, y2 star, zn star, delta v11, or v2, v12, n. And this kind of continues all the way until you get up to the final value, which is f of xn star, yn star, zn star times delta v and n. So it's worth noting that this is a triple summation. There's a lot of terms in this sum in general, and it grows even faster than the Riemann sum for double integration. So we don't really want to use this for computing the actual value of the triple integral. We're going to see that just like before in the double integral case, we can do this a lot quicker using what are called iterated integrals. But this Riemann summation formula is very important for approximations sometimes, and also dealing with functions that have very complicated integrals. Sometimes it's more efficient to use a numerical approximation. But we define the triple integral of a function over a three-dimensional domain as the limit as n goes to infinity of this Riemann sum. As long as the limit exists, and the upper and lower sum limits for the lower sums of this Riemann sum approximation in the upper sums are equal to one another. The limit as n goes to infinity of ln is equal to the limit as n goes to infinity of un. Just like we defined it for the double integral as well, and the single variable integral. It's very, very similar. But this process is definitely a little bit more complicated in 3D because your domain is, in some sense, could be much more complicated than even a double integral domain. So we can take this idea of the triple integral and actually immediately using the Riemann sums prove a number of different very interesting properties of the triple integral. So the notation for the triple integral, like we said before, is if you have the triple integral of a function, some function, say g of x, y, z, you could write it like this. This is the standard notation. But you could also say, do the triple integral over omega of some function g of x, y, z. You could express dv as dz, dy, dx. This is just kind of a leftover result of the fact that in our Riemann sum, delta v ijk, the area of the volume of the ijkth rectangle in our Riemann sum, is delta xi times delta yj times delta zk. Okay, so these are two equivalent notations for writing a triple integral. We're going to see that evaluating a triple integral will be very, very similar to how we evaluate the double integral, with one extra step. Before we do that, we want to list some properties so we know that we're good. We can do relatively straightforward calculations with this triple integral. The first big property is called the constant property. And all of these properties can be shown with sum properties from the Riemann sum. So you kind of resort to using the Riemann sum to show all of these properties. But this says that the triple integral over a three-dimensional region of some constant times a function of x, y, and z. This is, assuming the integral of the function exists. This is the same thing as a constant, or that constant c, times the triple integral of the function. Or constants can be factored out in some sense. They slip through this integration procedure. This is very similar to this property for double integrals, and also this property for single integrals as well. The next property is called the sum difference property. And again, all of these properties are very, very similar to their double integral and single integral counterparts. But if you take the sum or the difference of two functions of three variables, so some function f of x, y, z plus or minus some function g of x, y, z, and you take the triple integral of that, this is going to be equal to the triple integral of the first function plus or minus the triple integral of the second function. So we can use this as a very big simplification in a lot of times, where sometimes you have two functions that are added together, and you want to say just focus on the individual triple integrals because you know how to evaluate those. You can use this to simplify in scenarios like that. The third big property that we have is the following. It's going to be, you can call it like a domination property. And the idea is that if for some, so let's say that for all points in omega, in our three-dimensional region omega, let's assume that the function f of x, y, z is always above, or bounds the function g of x, y, z above. Another way of saying that is that it dominates the function g from above. So it's always bounding the function g from above. If this is true, then we also have that the triple integral of the function f will also be greater than or equal to the triple integral of the function g. So this is the domination property. Which again, all of these properties are extremely similar to the counterparts for the double integral. And the justification for these are very similar. You use the Riemann sums, and then you just take the limit of the Riemann sums, and you use what you know about the limit of sequences. So these properties are relatively straightforward to show for finite sums. So the idea is that you use that property then in the limit to get these results. So this is the domination property. And the fourth main property is called the additivity property. which is again very similar to the additivity property for both single variable integrals and double integrals. The main idea is that if you have some domain omega in 3D, say this is our domain omega, it's a three-dimensional domain. You can split this domain, so we'll assume that we split it, say, into some complicated way, where the right half or one half of the domain we'll call omega 1. That's, say, this section in blue right here, this that I'm highlighting right now. And then we split it into the second section, which we'll call omega 2. So we'll highlight that in red right here. So for any region in 3D, if we split it into two separate pieces, right, then the integral, the triple integral of a function over the region omega is going to be equal to the triple integral over the first piece, omega 1, plus the triple integral over the second piece, omega 2. This is called the additivity property. It says that we can kind of, if we're looking for an individual triple integral, sometimes you have a very complicated domain. It makes more sense when you're evaluating the triple integral to split that domain up into multiple different pieces and do the triple integral over each individual piece individually. This is very useful for piecewise functions, right? Just like it is for the double integral and even the single variable integral, right? This additivity property is extremely important for simplifying integrals and simplifying calculations. So one of the big applications that we have is for volumes. We talked about how to do the volume of a region with the double integral. Well, it turns out that we can get the volume a little bit, in some sense, more directly using the triple integral. So volume. Say volume of a region omega using the triple integral. So this the idea that we're going to actually kind of use right here is very similar to how we showed that the area can be calculated using the double integral. So the volume of a region in 3D, omega, will always be equal to the triple integral over that region omega of the constant function 1. This is very similar to how in 2D we showed that the area of a region R was just equal to the double integral over that region of the function 1, the constant function 1. You'll recall that this is one of the first properties we showed of the double integral. So this directly holds for triple integrals as well. That the total volume of a region omega is exactly the triple integral of that region. The justification for this is, like pretty much every other property we're going to use, the justification comes from the Riemann sum. Right? If you consider the Riemann sum for the constant function 1 of this triple integral, it's the sum from I equals 1 to n, the sum from j equals 1 to n, and the sum from k equals 1 to n of 1 times delta xi delta yj delta zk. Or better yet, it's just the sum of the volume of the ijkth rectangle. So it's the sum of delta v ijk, which is approximately equal to the total volume of omega. If you go back to that picture that we looked at before, consider all of these rectangles, or not rectangles, all of these rectangular prisms that form the partition, extending all the way over the entire region omega. On the boundaries, you're going to have some rectangles that overlap the boundary, or some rectangular prisms that overlap. So when you add up the volume of all of these rectangles, you'll get an error. It's not the exact value of the volume, but as these rectangles get smaller and smaller and smaller in the limit, you're getting closer and closer and closer to the exact volume. So this is a nice justification of why the triple integral of the function 1 is exactly equal to the volume of that region. This is our first big application here, and this is also directly justified in some sense. It comes, you can think of it as coming from property 3, the domination property, because if you have the function 1 is always greater than or equal to 0, so the triple integral of that function 1 is also always going to be greater than or equal to 0 from the domination property. So we have a number of other different applications that we can give for this triple integral. We'll talk about the applications in a second. I'd say probably the most important application that to start off with is talking about the average value and the mean value theorem, both of which can be extended to three-dimensional domains, just like for the double integral. So we say that the average value of a function of three variables over a domain omega is given in the following way. We say that we'll denote it as, say, average of f. And we say that this is the total accumulation of the function in omega, so in the region omega, divided by the size of the domain omega, which is exactly the same idea that we use for the average value of a single variable function and also for a function of two variables in 2D. And we've just defined what it means to take the accumulation of a function in some region omega That's the triple integral of the function. So the average value of a function on some region is the triple integral of that function over the region omega. And this triple integral has to be divided by the size of the region omega, which ends up being, I'll put size in quotation marks here, if this is a region in 3D, which it is, the size is the volume of the region omega. So it's going to be the triple integral over omega of the function 1 dv, as we just talked about and just justified. So this is it. This is how you calculate the average value of a function. If you need to figure out the average value of any function, you take its integral over the region, its triple integral over that three-dimensional region, and you divide by its volume, the volume of the region omega. So both of these things you can calculate if you know how to calculate a triple integral. Just like before, you can use this idea to actually state the mean value theorem in the exact same way as you did for a double integral. So the mean value theorem can be extended for functions of 3 variables as well as for functions of 2 variables. I'm not going to review the mean value theorem in 1D or in 2D because we talked about that in a previous lecture, but the mean value theorem for a function of 3 variables on a domain omega is the following. So if f is a continuous function on a closed and bounded domain omega, in 3D, then the mean value theorem states that there exists at least one point you can call this point xi eta nu, such that the value of the function at the point is equal to the average value over omega. So at some point xi eta omega, where x is xi, eta is, y is eta, and z is nu, so xi eta nu, the value of the function at that point is equal to the average value of the function, or the triple integral of f over the volume. And this, again, just like before, allows us, you can rewrite this as the triple integral over a region will always be equal to the function at this point, or points, times the volume of the region This equality is saying it's the same. This expression is the same thing as this expression, and because the region omega is assumed to be a closed bounded domain, this function will have a maximum and a minimum value. So you can use that to say that the triple integral of a function over any region will always be bounded by m, where m is the maximum over omega of the function f. So m times the volume, and it'll always be bounded below by lowercase m times the volume. Right, so every triple integral has to be bounded by these two things. So where m is the maximum over omega of the function f, and lowercase m is the minimum of the function over the region omega. This is almost exactly similar to, I'd say, pretty much exactly similar to the double integral result, only it's using a triple integral over a three-dimensional region. But this is a statement of the mean value theorem, and it's very, very useful in general. You can use it to, say, figure out what the range should be for a given triple integral. You can use it to check calculations, but you can also use it in many other much more advanced scenarios and applications. So it's a very important thing to know. But the two main takeaways is that the average value formula, right, is very, very similar to before. It just involves calculating a triple integral and calculating a volume. So two separate triple integrals. There's a triple integral of the function f to calculate this. It's in the numerator, and the triple integral of the function 1 over the region omega. But if you can do that, you can calculate the average value of a function on any given region. So our big question is, how do we evaluate? A triple integral. Luckily, if you're okay with the double integral and how we evaluate the double integral, evaluating the triple integral is going to be the exact same procedure, or I should say very, very similar, with a little bit more of a complication when it comes to non-rectangular domains. But we'll start with the easiest type of domains, which is the rectangular domain. So we'll say, we'll start with a rectangular domain and the notation for this is very, very similar to our previous notation. Omega is equal to, say, the interval from a to b across the integral from c to d and the interval from e to f, say. A rectangular domain is the easiest way of evaluating the triple integral. Non-rectangular domains are more complicated, but we'll start with the basic rectangular domain first, and then move into non-rectangular domains in the next lecture. So this is the region, say, from A to B in X, the region from C to D in Y, and the region, say, from E to F in Z. So this is going to correspond to the definite integral over a region omega in 3D, which looks like this. So the triple integral over the region omega for this function of 3 variables is the same thing as the triple integral over the region omega dv is dz dy dx. And the way that we evaluate this integral is by considering the iterated integrals again. For a rectangular domain, x is going from a to b, which is a constant to a constant. Y is going from c to d, which is a constant to a constant. And z is going from e to f, which is a constant to a constant. So we can break this up into 3 separate integral procedures. Just like we did for the double integral, only the double integral we only had 2 separate integration procedures. You had an inner integral and an outer integral for the double integral. For the triple integral, we have an outer integral, or an outer iterated integral. We have a middle integral. And we have an inner integral. So just like before, where when we determine the bounds, when you determine the bound, which is kind of like step 1 of doing an integral, you have to move from the outside in, and we'll see that that's a very important procedure when we get to not integrating over non-rectangular regions in 3D. You have to determine the bounds by going from the outside in. But when you evaluate the integral, so that's step 2, you move from the inside out. The idea is you do the inner integral first. That's going to be, in this example, or in this order of integration, it'll be the z integral first. And then once you do that integral, you'll obtain a function of x and y. Z goes away because it's a definite integral, so the z is going to go away once you evaluate the inner integral. So you do the inner integral first, which is just the z integral. Then you do the middle integral of that result, which will make the y go away in this order of integration, because it's a definite integral with respect to y. And then lastly, after those first 2 integrals, you do the final integral, the outer integral, which is the integral with respect to x. And the number that you get, the value that you get after doing that, is the triple integral of that function over the region. So we'll see that for non-rectangular domains, this becomes, you have to be very careful, just like we did before. But we'll see that Fubini's theorem still holds. We can still switch the order of integration in any order of integration that we want, and that'll be covered in the next lecture. So let's end though with at least one or two examples of the triple integral over a rectangular region. So we'll start by considering the following triple integral. We'll do the triple integral of the function xyz is equal to we'll just take a relatively simple function. We'll do y times sine of z over, find the triple integral of this function over the domain, which is a rectangular domain for x from 0, or we'll do z from 0 to pi over 6, x from -2 to 3, y from 0 to 1. So the rectangular prism for x from -2 to 3, y from 0 to 1, and z from 0 to pi over 6. So the triple integral over this region omega of this function is going to be the iterated integral of y sine of z x here is going from -2 to 3. As x goes from -2 to 3, y is going from 0 to 1, and z is going from 0 to pi over 6. So we break this up and do the inner integral first. The inner integral is going to be the antiderivative of sine y times sine of z with respect to z, and the antiderivative of y sine of z is going to be negative y cosine of z, evaluated from pi over 6 to 0. Is the integral from -2 to 3, integral from 0 to 1. This is going to be, when we plug in here, you'll get negative y cosine of pi over 6, and you'll get minus negative y cosine of 0. So when you plug in here, that ends up becoming positive y cosine of 0, which is just 1. Y times 1 minus y times cosine of pi over 6. And that's our inner integral, so we just evaluated the inner integral right here. This is the same thing as y times 1 minus cosine of pi over 6. Cosine of pi over 6 is square root of 3 over 2. So this is y times 1 minus the square root of 3 over 2. So this is just constant. So this is the same thing as using our property 1, we can factor out the constant 1 minus square root of 3 over 2 and just focus then on the double integral from -2 to 3, from 0 to 1 of y dy dx. This is equal to 1 minus the square root of 3 over 2 times the integral from -2 to 3 of, well, the integral of y from 0 to 1 with respect to y. This is the middle integral now. This is going to be equal to y squared over 2, because that's the antiderivative of the function y from 1 to 0, which just becomes 1/2 minus 0, or 1/2. We can factor that out. This will become then 1/2 times 1 minus the square root of 3 over 2, which is the same thing as 2 minus the square root of 3 over 2, times the integral from -2 to 3 of 1, which is 2 minus the square root of 3 over 4. The antiderivative of 1 is just x, from 3 to -2. So our final answer is going to be 2 minus the square root of 3 over 4 times 3 minus -2, or 5. So it's 5/4 times 2 minus the square root of 3. This value is exactly the triple integral of the function that we started with, or the accumulation of that function inside this rectangular domain. If you'd want to figure out the average value of this function over the domain, you'd have to figure out the volume of the domain, in this case the triple integral of the constant function 1, or the triple integral from -2 to 3, from 0 to 1, and from 0 to pi over 6 of 1 dz dy dx, which you can I recommend you do on your own. It's even simpler than the integral that we just did. The idea, though, is that this ends up becoming exactly pi over 6 minus 0 times 1 minus 0 times 3 minus -2, or 5 pi over 6. That's the volume of this region, because it's a rectangular region, so it's just the length times the width times the height of this rectangular prism. So from our average value formula, then, you can use this for the average value of the function if you want to find that. The average value of this function is going to be on the region, is going to be given by this 5/4 times 2 minus root 3, which is the accumulation of the function, divided by 5 pi over 6, which is the total size of the region. So the average value of this function is going to be exactly 3 times 2 minus square root of 3 over 2 pi. This shows you how to apply that formula that we went over before, the average value of the function. So you could also apply the mean value theorem here as well. You can use this idea to calculate the maximum value and the minimum value of that integral. But this function is simple enough that we can actually just calculate the integral, and we did so. But it's nice to kind of see that be applied. We'll do one more example. We'll do the triple integral, say, over the rectangular region from 0 to pi, 0 to pi, and 0 to pi of the function cosine of u plus v plus w dw dv du, which is just in not x, y, z variables, but we'll show that you can use really whatever variables you want to use here, and this will be kind of an important idea when we start talking about integration in multiple with different coordinate systems in the next lecture. Let's say we want to take this integral right here. Well, our inner integral here is this first integral with respect to w. So we need to do this integral first with respect to w. So this, the value of this integral, the entire integral, will be integral from 0 to pi, 0 to pi, and then the antiderivative of cosine of u plus v plus w with respect to w is going to be sine of u plus v plus w. This is evaluated from w equals pi to w equals 0. So this will be the double integral of sine of u plus v plus pi minus sine of u plus v plus 0, which is just sine of u plus v, dv du, which is the same thing as the double integral I believe we can do all, so you could split it up into two parts. I think the easiest way for me to do this and not write too many steps, to not overwhelm me with the number of steps, is just, well, the antiderivative, this integral right here is going to be with respect to a v. So the middle integral here is this integral with respect to v. Which is going to be the antiderivative of this function, which will be sine of, or not sine, but the antiderivative of sine is going to be negative cosine. So it'll be negative cosine of u plus v plus pi. And that'll be minus negative sine of u plus v. This has to be evaluated for v from pi to 0. For negative, not negative sine, negative cosine. So it's the integral from 0 to pi of negative cosine of u plus v plus pi plus cosine of u plus v. And this has to be evaluated from pi to 0. Which is going to be negative cosine of u plus pi plus v, pi plus pi, plus cosine of u plus pi. That'll be minus negative cosine of u plus 0, which is going to be u plus pi, plus cosine of u plus 0, which is cosine of u. And it's this entire integral, so it's the integral with respect to u. And this will be the integral from 0 to pi of negative cosine of u plus 2 pi plus 2 times cosine of u plus pi minus cosine of u du which is going to be equal to the antiderivative of cosine of u plus 2 pi is going to be sine of u plus 2 pi, and you have a negative sign right there, so that has to stay there. Antiderivative of cosine of u plus pi is going to be sine of u plus pi. And the antiderivative of cosine of u is going to be sine of u. Evaluated from pi to 0. And so finally, to get this value, this will be, when we plug in, we'll get negative sine of pi plus 2 pi, or sine of 3 pi, plus 2 times sine of 2 pi minus sine of pi. And this is going to be minus sine of 0, negative sine of 0 plus 2 pi, which is 2 pi plus 2 times sine of 0 plus pi, but sine of pi minus sine of 0. And sine of 3 pi is 0, sine of 2 pi is 0, sine of pi is 0, sine of 2 pi is 0, sine of pi is 0, sine of 0 is 0. So this definite integral is going to be 0, which means the accumulation of this function, cosine of u plus v plus w, inside the rectangular prism from 0 to pi along x, 0 to pi along y, and 0 to pi along z, this triple integral, this accumulation is 0. I mean, the total amount of positiveness of the function kind of cancels out the total amount of negativeness of the function. Now this is an interesting example because you can actually see this if you, say, do a density plot of this function. Right? Same thing with 2D functions as well. If the double integral or the single variable integral is 0, the double integral is 0, the triple integral is 0, it means that the total amount of positiveness of the function cancels out the total amount of negativeness of the function. So there's a net accumulation of 0. So viewing a plot of this function, we can clearly see that this function, this is the function cosine of x plus y plus z. It has level surfaces which are planes of constant value. When you look at the level surfaces of this function, this is here the x-axis from 0 to pi over to pi, the y-axis here from 0 to pi, and the z-axis from 0 to pi. This is the axis right here. So the origin is right here. This is the x-axis, the y-axis, and then the z-axis. And I've done one of our density plots, so one of our plotting methods. This is using my custom Python code. And this basically takes a large number of points. I have 50 points along the x-axis, 50 points along the y-axis, and 50 points along the z-axis. So that's going to be 50 cubed. That's how many points are plotted here. And basically I've colored the function of each individual point to be the value of the function. So the value of this function, cosine of u plus v plus w. I guess the x is u, y is v, and z is w. So the value of the cosine function is indicated by color at every point, where dark red is 1, dark blue is -1, and the range of values in between are the range and values of that function. So you see very clearly that this function's, it starts here at 0, the origin, at 1. Then as you move away from the origin, the function gets closer and closer and closer to -1. And then as you move around in the domain, you get further and further away from -1 back to +1. And then as you get to the point 1, 1, 1, not 1, 1, 1, but pi, 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 you get closer and closer and closer to -1 again. That would correspond to, at this point, it would be, the function would be cosine of pi plus pi plus pi, or cosine of 3 pi. So the idea here is, though, that you see that even though it's a three-dimensional domain, the function has an equal amount, it looks like in 3D, of negative values and positive values. And this is why that the double integral of this, or the triple integral of this function over this region, ends up being 0, because the total amount of accumulation of the function in this region is 0. The total positive accumulation of the function cancels out the total negative amount of accumulation, resulting in a net value of 0 for the net accumulation in the region. So this is a really nice example, both because it's a relatively simple triple integral to calculate, but also because we can visualize it like this and really see what it means for the triple integral of a function to be 0. And the same interpretation also works for a double integral as well. But so that will conclude the lecture for today, though. This example is the last thing I wanted to show in the lecture today. Thank you very much for tuning in and listening, and I hope you had a great day.